Hey, my friend, if your mind feels full and the day has been heavy, you're in the right place. Tonight, I'll guide you through the hidden rhythms of the universe, slowly, calmly, and in a way that helps you drift toward rest. So settle in, take a deep breath, and let the quiet science of the cosmos carry you to sleep. Chapter 1. What is an oscillation? The quiet rhythm beneath nature. When physicists talk about oscillations, they are describing something very simple and very deep at the same time. An oscillation is a repeated variation of some quantity around a central value, often in time, moving back and forth between different states or positions. A pendulum that swings to one side and then to the other, a mass bobbing up and down on a spring, or an electric signal that rises and falls in a regular pattern are all examples of oscillatory motion. In more formal language, oscillation is a repetitive or periodic variation of a system about an equilibrium point or between a set of states, and it appears in almost every area of physics and science as a whole. To understand why oscillations are so important, it helps to start with the idea of equilibrium. Imagine a system in which there is some preferred configuration where all the forces balance. This configuration is called the equilibrium state. If you disturb the system slightly, perhaps by pulling a mass on a spring away from its resting position, or by nudging a pendulum so that it is no longer hanging straight down, the system will feel a restoring influence that tends to pull it back toward that equilibrium. In many systems, that restoring influence is proportional to how far you have displaced the system. The farther you pull the mass, or the more you tilt the pendulum, the stronger the restoring tendency. When the restoring effect is directly proportional to displacement and always directed toward equilibrium, the resulting motion is called simple harmonic motion, a particularly elegant type of oscillation. The essential feature of an oscillation is this back and forth exchange. When a mass on a spring is displaced and released, it accelerates toward the equilibrium position under the influence of the restoring force. As it moves, it picks up speed, converting stored potential energy in the spring into kinetic energy of motion. At the equilibrium point, the spring is momentarily uncompressed or unstretched, so the potential energy is at a minimum, but the speed of the mass is at a maximum. Because of that speed, the mass does not stop at equilibrium. It overshoots and compresses or stretches the spring in the opposite direction. Now, the kinetic energy is gradually converted back into potential energy as the spring resists the motion. At the turning point on the other side, the speed drops to zero, the potential energy is at a maximum again, and the whole process reverses. This continuous exchange of energy between kinetic and potential forms is at the heart of harmonic oscillation and provides a useful way of thinking about many kinds of vibrations. Although the detailed mathematics of harmonic motion involves differential equations and trigonometric functions, the qualitative picture is surprisingly simple. In the idealized case of a simple harmonic oscillator with no friction or other losses, the motion repeats itself perfectly, tracing out a smooth sine wave in time. The displacement from equilibrium varies in a regular pattern. The velocity and acceleration follow the same rhythm, but shifted in phase, and the total mechanical energy remains constant, merely flowing back and forth between its kinetic and potential forms. Even without equations, you can imagine this as a perfect, unending rhythm, like an ideal clock that never runs down. In real systems, of course, Friction and other dissipative processes are always present, gradually converting some of the mechanical energy into heat in the surroundings. This is called damping. Damped oscillations do not continue forever. Their amplitude slowly shrinks with time, even though the underlying tendency to oscillate remains. One of the profound reasons oscillations are so widely used in physics is that many systems, even very complicated ones, behave like harmonic oscillators when they are only slightly disturbed from equilibrium. If you examine a stable system and look at small deviations around its minimum energy configuration, the restoring forces often turn out to be approximately proportional to displacement. In mathematical terms, the potential energy function can be expanded near the minimum, and the lowest non-trivial term in that expansion is quadratic in the displacement, which leads directly to harmonic motion. This idea, sometimes called the small oscillation approximation, means that the simple harmonic oscillator serves as a universal model for small vibrations around stable equilibria across physics, from atoms in a crystal lattice to macroscopic mechanical devices. Oscillations also provide a natural way to describe how energy and information move through space. When you connect many oscillators together, for example, atoms in a solid or masses linked by springs, a disturbance at one point can set off a wave that travels through the system. Each individual component oscillates around its equilibrium position, but the pattern of oscillation, the wave, carries energy from one region to another. Sound in air can be understood as rapid oscillations of air pressure and particle positions that propagate outward from a source like a vibrating string or vocal cords. Ocean waves are oscillatory motions of water, with each parcel of water moving in a small orbit while the wave pattern itself travels across the surface. Light is an oscillation too, though of a different sort. It is an electromagnetic wave in which electric and magnetic fields oscillate in space and time and can propagate even through the vacuum. In all of these cases, the underlying concept is the same. Something is rhythmically varying about a central value, and that variation forms a pattern that can propagate. On the microscopic scale, oscillations acquire a quantum character. Quantum mechanics tells us that the energy of bound systems like atoms and molecules is quantized. They can only occupy discrete energy levels. The harmonic oscillator appears here as well, but now it is a quantum harmonic oscillator, a system whose allowed energy states are evenly spaced, separated by a fixed quantum of energy. Remarkably, in the quantum version, the lowest possible energy is not zero. Even in its so-called ground state, the oscillator retains a non-zero energy, often referred to as zero-point energy. This reflects the Heisenberg uncertainty principle. The position and momentum of a quantum object cannot both be precisely known, so the system cannot sit perfectly still at the bottom of the potential well. There is always some residual jitter, a tiny but unavoidable vibration built into the fabric of quantum systems. From the perspective of quantum field theory, which is our best framework for describing elementary particles and their interactions, oscillations become even more fundamental. In this picture, what we think of as particles are actually excitations or quanta of underlying fields that permeate space. Each field can be thought of as a vast collection of coupled quantum harmonic oscillators, one at every point in space. A particle, such as an electron or a photon, is not a little billiard ball but a particular vibrational state of its corresponding field. The vacuum itself, even when no particles are present, is not truly empty, but filled with the zero-point motions of these quantum oscillators. In that sense, the view that everything is, at some level, vibration is not merely poetic. It is closely tied to the way modern physics models reality. It is also useful to distinguish between free oscillations and forced oscillations. A free oscillation is what you see when a system is displaced and then left alone to move under its own internal forces, like a plucked guitar string vibrating freely. A forced oscillation occurs when an external periodic influence continuously drives the system, such as a child being pushed on a swing at regular intervals. If the driving frequency matches the system's own natural frequency, the oscillation amplitude can grow dramatically. This is resonance. Even though resonance will be discussed in more depth later, it is worth noting here because it highlights how delicate and powerful oscillatory behavior can be. When the timing is right, energy flows efficiently into the oscillation, building up large responses from comparatively gentle nudges. It is important to remember, however, that real oscillations are rarely perfectly harmonic. Nonlinear effects can distort the motion, damping can drain energy, and external influences can modulate the frequency or amplitude. In a lightly damped system, the oscillations persist for many cycles but slowly decay. In a heavily damped system, the motion may return to equilibrium without even completing a full oscillation. In driven systems, complex patterns such as beats or more irregular oscillations can emerge when multiple frequencies interact. Yet even in these more complicated circumstances, the simple harmonic oscillator remains a vital reference point, a baseline against which deviations are measured and understood. As you listen to this, you might notice that many aspects of your own experience follow quiet rhythms. Your heartbeat, your breathing, and even your patterns of thought and attention have their own natural oscillations. Day passes into night and returns again, seasons cycle, and the planet itself turns steadily beneath the stars. Physics shows that the universe, from the smallest quantum fields to the motion of galaxies, often prefers to express change in the form of gentle, repeating patterns. There is comfort in that idea. You are part of a world that tends toward rhythm and balance, a world in which disturbances are met with restoring forces, and motion often settles into calm, predictable cycles. For now, you can allow that thought to soften the edges of your day. Just as a simple oscillator gradually releases its excess energy and comes to rest near equilibrium, you are allowed to let your own internal motions slow and quiet. The problems and activities of waking life do not need to be solved all at once. They can ebb and flow like a gentle vibration, returning at another time. In this moment, it is enough simply to breathe, to follow the slow, steady oscillation of your own chest rising and falling, and to let your mind rest closer to its own equilibrium. Chapter 2. The Mathematics of Motion, Frequency, Amplitude, and Waveforms. When physicists describe oscillations, they often turn to a mathematical language not because it adds difficulty, but because it provides a clear, structured way to talk about repetition. Oscillations unfold in time, and mathematics allows us to capture how a pattern changes, returns, and repeats. Even without equations, the core concepts behind oscillations, frequency, amplitude, phase, and waveform, offer a way to trace the quiet order underlying many forms of motion. A good starting point is to imagine how an oscillating system moves in time. Suppose you track the position of something that vibrates, such as a mass on a spring or a point on a guitar string. If you plot its displacement from equilibrium as time passes, the path forms a smooth curve. In an ideal system, this curve rises, falls, crosses the equilibrium point, dips into the opposite direction, and then climbs back again. The pattern repeats, and the resulting shape is what physicists call a waveform. The simplest and most fundamental waveform is the sinusoid, a smooth, continuous motion that represents the behavior of a perfect harmonic oscillator. A sinusoidal waveform is not just aesthetically pleasing. It reflects the underlying physics of many systems that prefer to move in the simplest possible way when disturbed. This simplicity arises because the restoring forces in such systems act proportionally to displacement. When something is nudged away from equilibrium, the force pulling it back increases the farther it goes. This relationship naturally creates a smooth, rhythmic motion. The waveform is a visual expression of that rhythm, allowing us to see how the motion cycles through its peaks and troughs. One of the defining features of any waveform is amplitude. Amplitude describes the maximum displacement of the system from its equilibrium position. In mechanical systems, it is the farthest distance a pendulum swings or the largest stretch of a spring. In sound, amplitude relates to loudness, in light to brightness. Though different systems store and release energy in different ways, amplitude always reflects the size of the excursion from equilibrium. Larger amplitude means more energy is present in each cycle, whether that energy is kinetic, potential, acoustic, or electromagnetic. The temporal character of oscillation is captured by frequency. Frequency tells us how many cycles the system completes in a given time. A rapidly vibrating tuning fork has a high frequency. A slowly rocking buoy on the ocean has a low frequency. Humans perceive these frequencies directly in many contexts. High-frequency sound is heard as a high pitch, while low-frequency sound gives a deeper tone. For light, frequency determines color, with higher frequencies shifting toward violet and lower frequencies toward red. These perceptions arise from the underlying physics of how waves interact with sensory systems. But the concept of frequency itself simply describes how fast an oscillation repeats. Closely connected to frequency is the period of the oscillation, the duration of a single complete cycle. The two are inversely related. Describing motion in terms of frequency or period is simply choosing whether we focus on the rate of cycles or the length of each one. Although no numeric expressions are used here, it is enough to understand that high-frequency oscillations have short periods, and slow oscillations have long ones. This dual perspective appears in nearly all branches of physics, from acoustics to planetary dynamics. Where waveform becomes especially powerful is in the description of complex patterns. Real systems rarely oscillate with a perfect sinusoidal shape. A musical note from a violin, for instance, is rich with additional components called harmonics. Each harmonic is itself a sinusoidal oscillation, vibrating at a frequency that is a whole number multiple of the fundamental tone. Together, these harmonics produce the characteristic timbre of the instrument. A mathematical method known as Fourier analysis shows that any repetitive waveform, no matter how intricate, can be represented as a combination of simple sinusoidal oscillations. This idea ranges far beyond music. It is used in analyzing electrical signals, studying ocean waves, measuring vibrations in engineering structures, investigating stellar oscillations, and decoding patterns in climate data. The insight that complicated behavior can be decomposed into simple oscillations is one of the foundational principles that allow scientists to explore complex systems with clarity. To fully describe an oscillation, one must also understand phase. Phase indicates where in its cycle the oscillation is at a given moment, whether it is rising toward a peak, descending toward equilibrium, or reaching a minimum. Consider two identical oscillators. They may have the same amplitude and frequency, but one may reach its peak slightly earlier than the other. This difference is a difference in phase. Phase relationships matter because when oscillations interact, the resulting motion depends on how their phases align. When two waves with matching frequencies and aligned phases combine, they reinforce one another, increasing amplitude. When their phases are opposite, they cancel. This phenomenon, known as interference, is essential in optics, acoustics, and quantum physics. Interference patterns in light create the colors seen in thin films or the fine fringes of diffraction experiments. In sound, interference can produce zones of amplified or diminished intensity. In quantum systems, interference reflects the wave-like nature of matter itself. Oscillations can also travel through space as waves. When you disturb a stretched rope or a pool of water, a ripple forms and moves outward even though the medium itself does not flow forward. Each point in the medium oscillates around equilibrium, but the pattern travels, carrying energy from one place to another. The mathematics of waves ties together the time-based nature of oscillation with its spatial form. A wave possesses both a temporal frequency and a spatial wavelength, the distance between consecutive peaks or troughs. Although we avoid formal expressions, the connection between frequency, wavelength, and propagation speed is one of the most important relationships in wave physics. It explains how sound moves through air, how light propagates through space, and how waves in plasmas, solids, and fluids transmit energy across large distances. Electrical oscillations offer a parallel to mechanical ones. In a circuit containing inductive and capacitive elements, energy oscillates between electric and magnetic fields. The current and voltage rise and fall in time, tracing out sinusoidal patterns, much like the motion of a mechanical oscillator. The frequency of these electrical oscillations is determined by the properties of the circuit elements, and the analogy between mechanical and electrical oscillators has been central to the development of radio communication, signal processing, and the generation of stable time standards. Although these systems operate on different physical principles, the underlying mathematics of oscillation connects them. When we turn to more advanced systems, oscillations reveal even richer structure. Many objects can vibrate in more than one way. A drumhead supports numerous vibrational patterns, each with its own natural frequency. These vibrational modes correspond to specific spatial patterns that remain stable as they oscillate. Similar principles appear in quantum physics, where electrons in atoms occupy discrete energy levels that reflect allowed modes of the quantum wave function. In molecules, atoms vibrate and rotate in characteristic ways that reveal information about chemical bonds and internal structure. In astrophysics, stars pulsate in patterns that allow astronomers to infer their internal composition and temperature. Across these disciplines, the same mathematical ideas of frequency, amplitude, mode structure, and phase help describe behavior at scales ranging from atomic distances to the span of stellar atmospheres. Throughout all these varieties of oscillatory behavior, the mathematics of motion provides a coherent vocabulary. It allows physicists to compare systems that are outwardly unrelated but structurally similar. a radio receiver, the vibrating air in a concert hall, the trembling surface of a distant star, and even fluctuations in the early universe all express themselves through oscillations that can be analyzed using the same conceptual tools. Mathematics becomes the language through which nature's rhythms can be described, predicted, and understood. As you reflect on these ideas, there is something quietly reassuring beneath them. Oscillations appear everywhere, not because the universe needs to be complex, but because systems tend to return, to repeat, to settle into recurring patterns. In a way, the mathematics of motion describes the universe's preference for rhythm. And just as nature moves through gentle cycles, from the pulses of distant stars to the slow undulations of your own breath, you too are part of this quiet symmetry. You are allowed to rest within it, to feel the repeating patterns of your day soften into something calmer, something steady, something that reminds you that even in the vast machinery of physics, there is room for stillness. Chapter 3. Waves in Space, Light, Sound, and the Movement of Energy. When we talk about waves, we are really talking about patterns that move. A wave is not a thing in the traditional sense. It is a process, a disturbance, a shifting of some quantity that passes from one place to another. Waves do not carry matter from point to point in the way a thrown object does. Instead, they carry energy and information through the motion of something else, whether that something is air, water, electromagnetic fields, or even the curvature of space-time itself. The essence of a wave is this ability to transport influence without transporting the medium itself. This characteristic makes waves one of the most fundamental and unifying ideas in all of physics. Consider the surface of a still lake. If you touch the water with your finger, ripples form and expand outward. No individual water molecule travels with the ripple from the center to the edges. Each molecule simply oscillates around its own position, passing the disturbance along to its neighbors. The pattern moves. The substance does not. This is the hallmark of a wave. Although water waves are perhaps the most familiar example, they are only one instance in a family of wave phenomena that stretch from everyday experience to the most distant regions of the observable universe. Sound is another example of a wave, though it differs from water waves in important ways. Sound travels through the oscillatory motion of particles in a medium, typically air, but it can also propagate through solids and liquids. When an object vibrates, such as a guitar string or a set of vocal cords, it pushes and pulls the surrounding air molecules. Zones of higher and lower pressure form, moving outward in all directions. Each region of compressed or rarefied air is merely a temporary fluctuation, yet together they create a structured pattern that carries energy away from the source. What we experience as pitch corresponds to how rapidly these pressure variations occur, while loudness relates to their amplitude. Sound, in this sense, is the human experience of a physical wave moving through a medium. Light is a wave as well, though of a very different nature. Unlike sound, light does not require a medium of particles to support its motion. It can travel through air, through glass, and through the vacuum of interplanetary and interstellar space. Light is an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields. This picture emerged from the work of 19th century physics, which showed that electric fields and magnetic fields are deeply linked. When one changes in time, it induces the other, and the combined oscillation forms an electromagnetic wave that moves forward through space. Light is simply one range of frequencies within this electromagnetic spectrum, a band that the human eye has evolved to detect. Other frequencies, such as ultraviolet light, infrared radiation, radio waves, and microwaves, lie outside our direct perception but obey the same underlying principles. Across this entire spectrum, waves are the carriers of energy and information. The behavior of waves becomes especially interesting when they interact with obstacles or openings. If you shine a beam of light through a narrow slit, the light spreads out rather than forming a sharp line. This phenomenon, called diffraction, is a direct consequence of the wave nature of light. Sound exhibits diffraction too. You can hear someone speaking around a corner because sound waves bend and spread as they encounter edges. Water waves spread when they pass through gaps in breakwaters. This bending is not an imperfection. It is a fundamental feature of wave behavior. Diffraction reveals how waves distribute energy across space, adjusting to the geometry of their surroundings in a smooth and continuous way. Reflection provides another example of wave behavior. When a wave encounters a boundary, it may bounce back. Light reflects from mirrors, sound reflects from walls to form echoes, and ocean waves reflect from cliffs and breakwaters. Reflection preserves the structure of the wave, though its direction changes. If the boundary is smooth and flat, reflection occurs in a predictable way. If the boundary is irregular or rough, the reflected waves scatter into many directions. Reflection shapes how we perceive the world. Mirrors create images through controlled reflection, and architectural acoustics uses reflection to enhance or dampen sound in a concert hall. Even on astronomical scales, reflection plays a role. Clouds of cosmic dust reflect starlight, helping astronomers trace the structure of regions otherwise invisible. Refraction occurs when a wave changes direction as it moves from one medium into another. When light enters water from air, its path bends because the speed of light in water is lower. This bending causes a straight object partially submerged in water to appear bent at the surface. Refraction explains the focusing action of lenses, which bend incoming light to form images. Sound refracts too, bending as it moves through regions of air with different temperatures or densities. Ocean waves refract as they encounter varying water depths, curving towards shallower regions. Refraction reveals how waves respond to changing environments and forms the foundation for technologies such as eyeglasses, telescopes, cameras, and fiber optic communication. Waves can interfere with one another, creating regions where they reinforce or cancel. When two waves of the same type meet, their amplitudes combine. If their peaks coincide, the resulting amplitude grows larger, a process called constructive interference. If the peak of one coincides with the trough of the other, they cancel, producing destructive interference. We experience such effects in many forms. Noise-canceling headphones use destructive interference to suppress unwanted sounds. Soap bubbles shimmer with colored patterns because light waves reflecting from different surfaces interfere with one another. In experiments involving very narrow slits or extremely sensitive measurements, interference reveals the precision and coherence of wave behavior at small scales. These patterns are not simply aesthetic. They demonstrate the ability of waves to superpose, a property that plays a central role in quantum mechanics. Energy flow in waves is another essential idea. When a wave moves, it transports energy without transporting matter. The amount of energy carried depends on the wave's amplitude and frequency. High-amplitude waves carry more energy, which is why large ocean waves can break forcefully against the shore. Higher-frequency electromagnetic waves, such as ultraviolet radiation, carry more energy per oscillation than lower-frequency waves like radio waves. This ability to transport energy allows waves to perform work at a distance. The warmth you feel from sunlight is the result of energy carried across millions of kilometers of space by electromagnetic waves. The sound of distant thunder is the energy of pressure waves traveling through the atmosphere. Even the gentle ripples on the surface of a lake represent the transport of energy from wind or falling droplets. Although classical waves like water waves, sound waves, and light waves are familiar, more exotic waves exist as well. In solid materials, atoms form repeating structures known as lattices. Vibrations in these lattices propagate as waves called phonons, which play an important role in heat conduction and material properties. In plasmas, waves arise from the collective behavior of charged particles interacting through electric and magnetic fields. In astrophysical environments, waves can travel through the ionized gas surrounding stars or through the dense plasma of magnetospheres. These waves follow the same principles as other waves, but reflect the complex interplay of forces in their respective systems. The most astonishing waves discovered in recent decades are gravitational waves. Predicted by the theory of general relativity, gravitational waves are oscillations in the curvature of space-time itself. When massive objects accelerate, such as merging black holes or neutron stars, they disturb space-time in a way that propagates outward, much like ripples on a pond. These waves are incredibly subtle, stretching and compressing space-time by amounts so small that only the most sensitive instruments can detect them. Yet their detection confirmed a profound aspect of nature. Even space-time can vibrate. Gravitational waves carry information about events that cannot be observed through light alone, opening a new window into the universe's most extreme environments. Across all these examples, a unifying truth emerges. Waves arise whenever a system has a way to store energy in more than one form and convert between those forms as time passes. For sound, energy oscillates between regions of compressed and rarefied air. For light, energy oscillates between electric and magnetic fields. For ocean waves, gravitational and kinetic energies exchange as the water surface moves. For gravitational waves, space-time curvature itself oscillates. These processes root wave behavior in the fundamental laws of physics, ensuring that waves appear across scales from the smallest particles to the largest cosmic structures. The mathematics of waves, though not explicit here, helps describe how these patterns travel, how they grow and diminish, how they interact, and how they carry meaning. Without waves, communication across distance would be nearly impossible. Life depends on waves. The light that fuels photosynthesis, the sound that allows communication in animals, and the electromagnetic radiation that warms Earth. Even the signals within the human nervous system rely on wave-like propagation of electrical impulses. Waves are nature's way of transferring influence across space. As you reflect on these ideas, it becomes clear that waves are not just features of the external world. They are woven into the structure of existence itself. Every moment you perceive is shaped by waves arriving from countless sources. Light from distant stars, sound from your surroundings, the subtle waves of thought moving through the brain. Somewhere in this interplay of oscillations, you too are part of the pattern. Just as waves travel outward and fade into calm, your thoughts and emotions rise and fall, pass and return. In the vast movement of energy through the universe, there is space for stillness and space for you to rest within that quiet rhythm. Chapter 4. Atoms are vibrations, the quantum origins of motion. When we look at the physical world on the scale of human experience, things appear solid, still, and self-contained. A table does not seem to tremble. A stone does not appear to shimmer with internal movement. Even the air around us feels calm unless stirred by wind. Yet beneath this apparent stillness lies an extraordinary truth revealed by modern physics. Matter is never fully at rest. Atoms, the basic building blocks of all visible substances, are sites of continuous, structured vibration. Their constituent parts shift, oscillate, and exist in patterns of motion that arise not from external disturbances, but from the laws of quantum mechanics themselves. To understand this, it helps to begin with how atoms are arranged in matter. In solids, atoms are not free to wander. They occupy positions within a repeating lattice structure, held in place by electric forces that arise from the interactions between their nuclei and their surrounding electrons. Even though these forces bind atoms to particular regions, they do not fix them with absolute rigidity. Instead, each atom experiences a balance of attractive and repulsive forces that creates an equilibrium position. If the atom is nudged slightly from this position, it experiences restoring forces that bring it back down, much like a tiny mass on an elastic spring. This means that at the most basic level, atoms can vibrate around their equilibrium points. In classical physics, an atom at sufficiently low temperature could come to rest. The oscillations would decrease as heat was lost, eventually ceasing when the system reached absolute zero. Quantum mechanics, however, tells a different story. According to the Heisenberg uncertainty principle, the position and momentum of a particle cannot both be known with perfect precision. This limits how still an atom can become. Even at the lowest achievable temperature, atoms retain a residual amount of motion known as zero-point energy. Zero-point motion is not an optional feature of quantum systems. It is an unavoidable consequence of the mathematical structure of quantum theory. The atom cannot settle exactly at the bottom of its potential well because doing so would violate the fundamental uncertainty built into nature. These vibrational motions are not random. They occur at characteristic frequencies that depend on the mass of the atom and the strength of the restoring forces acting on it. Lighter atoms vibrate more rapidly, heavier ones more slowly. Stiffer bonds create higher frequency vibrations, while softer bonds yield lower frequencies. This behavior can be observed experimentally. When molecules absorb infrared radiation, the energy excites their vibrational modes. Each vibrational mode corresponds to a specific frequency, producing a unique signature that chemists can detect. These vibrational patterns reveal details about the structure and composition of molecules, demonstrating that even stable, familiar substances are alive with quantum motion. Within an atom, electrons do not orbit the nucleus like planets around a sun. Instead, they occupy standing wave patterns that are solutions to the Schrödinger equation, the central equation of non-relativistic quantum mechanics. These standing waves, or orbitals, represent stable configurations of the electron's probability distribution. Each orbital has a shape, a characteristic energy, and a wave-like structure. The word vibration, in this context, does not describe electrons physically shaking around the nucleus. It describes the mathematical fact that electrons exist in wave-like forms. The shapes of these waves are determined by the constraints of quantum theory, and transitions between them occur in quantized steps. When an electron moves from a lower energy orbital to a higher one, it absorbs energy. When it returns to a lower energy state, it releases energy in the form of a photon. These transitions are a manifestation of deeply structured, inherently oscillatory behavior. In addition to the electronic vibrations within atoms, there are collective vibrations across entire materials. In solids, atoms connected by interatomic forces behave as coupled oscillators. The vibrations propagate through the lattice as waves, giving rise to quantized modes called phonons. Phonons are not particles in the classical sense. They are quantized excitations of lattice vibrations, representing discrete packets of vibrational energy. Phonons explain why heat moves through a solid, how sound travels within materials, and why certain materials conduct electricity differently when cooled. In fact, the thermal properties of many substances, from metals to crystals, depend on how phonons move and interact. These quantized vibrations reflect a deep relationship between atomic motion and large-scale physical behavior. Phonons also reveal the quantum mechanical nature of temperature. Temperature is often described as a measure of how fast atoms and molecules move. While this picture works reasonably well at everyday scales, quantum mechanics adds a layer of subtlety. The thermal energy of a substance arises from the occupancy of vibrational modes. At higher temperatures, more vibrational modes are excited and phonons proliferate. At lower temperatures, fewer modes are populated, but zero-point vibrations remain. This means that even the coldest achievable materials never become perfectly still. Their atoms and lattices retain faint, persistent tremors, motions that are an intrinsic part of quantum mechanical structure. Individual atoms also possess internal oscillatory behavior due to their subatomic components. The protons and neutrons within the nucleus are themselves composite particles made of quarks, bound together by the strong nuclear force. This force is far more intense than the electromagnetic force binding electrons to the nucleus, and it is mediated by particles called gluons. Within protons and neutrons, quarks are not static. They interact dynamically, exchanging gluons and moving in ways that can be modeled as confined oscillatory behavior within a potential well created by the strong force. Although this internal motion is fundamentally quantum and relativistic, the idea that subatomic particles exhibit structured movement forms another example of vibration at the heart of matter. Even the vacuum of space contributes to atomic vibrations. Quantum field theory suggests that fields permeate all space, and that these fields exhibit fluctuations even when they are in their lowest energy states. These fluctuations, often called vacuum fluctuations, can influence atomic systems. One well-known effect is the Lamb shift, a small difference in energy levels within hydrogen atoms that arises from interactions between the electron and the fluctuating electromagnetic field. Another example is the Casimir effect, where closely spaced metal plates experience an attractive force due to changes in the vacuum's allowable vibrational modes. These phenomena demonstrate that even empty space cannot remain truly static. It too vibrates at the level of quantum fields. When atoms combine into molecules, their internal vibrations become even more elaborate. A molecule with many atoms can move in several independent vibrational patterns, including stretching, bending, twisting, and wagging motions. Each of these motions occurs at specific energy levels. When a molecule absorbs infrared light, it transitions into a higher vibrational state. The frequencies of these transitions form an identifiable spectrum, allowing scientists to study molecules in distant nebulae or within biological tissues. Molecular vibrations influence chemical reactions, biological signaling, and the absorption of solar radiation in Earth's atmosphere. The greenhouse effect, for instance, arises partly because certain atmospheric molecules absorb and re-emit infrared radiation through vibrational transitions. In liquids, atomic vibrations remain, but they are complicated by the fluidity of the medium. Molecules still oscillate, yet they constantly shift, rotate, and collide with their neighbors. These motions create collective excitations that mix vibrational and translational behavior. The structure of a liquid is dynamic, with atoms and molecules vibrating within temporary cages formed by their neighbors before slipping past one another. This interplay contributes to viscosity, diffusion, and other macroscopic properties of fluids. At the quantum level, even the most fundamental particles are described using wave-like structures. Electrons, quarks, neutrinos, and other particles exhibit oscillatory behavior inherent to their quantum wave functions. In some cases, such as neutrino oscillations, particles can even shift between different identities as they propagate, a phenomenon arising from the wave-like interference of quantum states. These oscillations reveal new aspects of fundamental physics and challenge intuitive distinctions between particle types. When we consider these layers together, electron waves, nuclear vibrations, phonons, molecular vibrations, and quantum field fluctuations, a coherent picture emerges. Motion is not something added to matter. Motion is woven into matter. Vibration is not an occasional feature of atoms, but their default state. Every structure in the universe, from the smallest particle to the densest star, contains internal patterns of oscillation that express the laws of quantum mechanics. This perspective changes how we see the world around us. The solidity of a rock is the collective result of trillions of atomic vibrations in stable equilibrium. The warmth of sunlight on your skin comes from vibrational transitions within atoms releasing photons. The color of a flower arises from electron oscillations interacting with electromagnetic waves. The very air you breathe is alive with molecular vibrations too rapid for human senses to follow. What appears calm, still, and unmoving is, on a deeper level, constantly shifting and resonating. As you think about this, you might feel a subtle shift in perspective. The matter that forms your body, your surroundings, and the entire world is never static. It hums with invisible structure, encoded in the language of quantum motion. In a universe where everything vibrates, where even silence contains fluctuations, stillness is not the absence of motion, but a kind of gentle balance. And perhaps there is comfort in knowing that you too are part of this living pattern. Even in quiet moments, you are held within a world that moves softly, continuously, and without hurry, carrying you along in its endless and intricate rhythm. Chapter 5. Resonance. When the universe amplifies its own rhythm. Resonance is one of the most striking and elegant phenomena in all of physics. It appears whenever a system is capable of oscillating and is driven by an external influence whose rhythm matches the system's own natural frequency. When this alignment occurs, something remarkable happens. The system begins to respond with dramatically increased amplitude, sometimes with gentle, almost effortless motion, and sometimes with destructive intensity. Resonance represents the universe's tendency to amplify harmony, to strengthen vibrations that match its internal preferences, and to reveal hidden structures that are otherwise quiet or invisible. To understand why resonance happens, it helps to imagine a simple oscillator. Every oscillating system, from a swinging pendulum to an electron in a magnetic field, has a natural frequency determined by its physical properties. This is the frequency at which the system prefers to move when left to itself. If an external force acts on the system with a rhythm that does not match the natural frequency, the response is limited. The energy imparted does not accumulate efficiently. But when the external driving frequency matches the system's own, each push arrives at just the right moment to reinforce the system's motion. The result is a steady and amplified oscillation. A familiar example is a child on a swing. If the swing is pushed at random intervals, the motion remains small and inconsistent. But if each push arrives precisely as the swing reaches the peak of its backward motion, the energy from each push adds constructively to the previous cycle. The swing climbs higher with very little effort. This simple image captures the essence of resonance. Small, well-timed inputs can produce large responses. In physics, resonance is far more than a playground analogy. It appears in mechanical systems, electrical circuits, acoustic environments, atomic and molecular structures, and even astrophysical processes. Each system resonates in its own way, yet all are governed by the same underlying principles. Resonance reveals something deep about oscillating systems. They are sensitive to timing. They possess internal rhythms that make them receptive to some influences and nearly unresponsive to others. Mechanical resonance is perhaps the most intuitive form. A guitar string vibrates at specific resonant frequencies determined by its length, tension, and mass per unit length. When plucked, it produces a tone associated with its fundamental resonance and accompanying harmonics. But resonance also appears when the string is not directly touched. If you sing a note that matches the string's natural frequency, the string can begin to vibrate in sympathy, absorbing energy from the sound waves in the air. This sympathetic vibration shows how resonance allows energy to transfer through matching frequencies, even without direct contact. Another example is found in architectural acoustics. Rooms have natural resonant frequencies determined by their dimensions and the reflective properties of their walls. When a sound is produced at one of these frequencies, the room reinforces it, making certain tones seem louder or more sustained. This is why voices sound different in a small tile bathroom compared with a concert hall. Architects and acoustic engineers rely on an understanding of resonance to shape environments that support music, speech, or silence. Electrical resonance plays an essential role in communication technologies. A simple circuit containing an inductor and a capacitor can resonate, oscillating energy back and forth between electric and magnetic forms. When such a circuit is driven by an external voltage source, it responds most strongly when the driving frequency matches its natural resonant frequency. Radios exploit this principle. Tuning a radio to a particular station is essentially selecting the resonant frequency of an internal circuit so that it picks up one broadcast while rejecting others. Without resonance, separating signals in a crowded electromagnetic environment would be nearly impossible. Resonance also shapes the interactions of light with matter. Atoms and molecules absorb electromagnetic radiation most efficiently when the frequency of the incoming light matches the energy difference between quantized internal states. This frequency matching is a kind of resonance. When the frequencies align, the atom absorbs a photon and undergoes a transition to a higher energy state. When they do not, the light passes through with far less interaction. Spectroscopy, one of the most powerful tools in science, relies on this principle. By examining which frequencies of light a substance absorbs or emits, scientists can deduce its structure, temperature, and composition. The patterns of atomic resonance allow astronomers to determine the chemical makeup of distant stars, geologists to analyze mineral samples, and medical researchers to study biological tissues. Molecular resonance introduces even more complexity. Molecules vibrate and rotate in specific patterns, each with its own resonant frequencies. Infrared radiation is particularly suited to interacting with these vibrational modes. When infrared light resonates with a vibrational frequency of a molecule, absorption occurs. This is the basis of infrared spectroscopy, but it is also central to Earth's climate system. Greenhouse gases such as carbon dioxide and methane resonate with certain infrared frequencies emitted by the planet's surface, absorbing and re-emitting the radiation. This resonance-driven process contributes to the greenhouse effect, warming the atmosphere and influencing global temperature. On even smaller scales, resonance appears in atomic nuclei and subatomic particles. Nuclear magnetic resonance, the principle behind magnetic resonance imaging, relies on the fact that atomic nuclei with magnetic moments resonate at specific frequencies in the presence of an external magnetic field. By applying radio frequency pulses tuned to these resonances, scientists can manipulate nuclear states and detect the tiny signals they produce. This allows the mapping of soft tissues within the human body, revealing detailed physiological information without invasive procedures. Resonance is not merely a microscopic or technological phenomenon. It also appears in nature on scales as large as planets and stars. When meteors strike a planet, they can excite resonant modes that travel through the planet's interior. Observations of these seismic waves reveal the structure of planetary cores and mantles. The Sun and other stars experience oscillations known as stellar pulsations. These pulsations occur because energy from nuclear fusion interacts with the star's internal layers in resonant patterns. By analyzing the frequencies of these oscillations, astronomers can infer a star's internal temperature, density, and composition. This field of study, known as astroseismology, treats stars as giant resonant cavities whose vibrations provide windows into their hidden interiors. Resonance even influences the dynamics of orbital systems. In planetary systems, gravitational interactions can lead to orbital resonances. When the orbital periods of moons or planets are related by simple ratios, their gravitational influences reinforce one another in regular patterns. Jupiter's moons, Io, Europa, and Ganymede, exist in such a resonance. These interactions contribute to tidal heating, shaping geological activity on Io, and possibly maintaining subsurface oceans on Europa. Resonance helps stabilize or destabilize orbits, sculpting the architecture of planetary systems over millions of years. The destructive potential of resonance is also part of its story. When resonance causes amplitudes to grow unchecked, it can lead to structural failure. Historical examples include the collapse of bridges subjected to rhythmic forces matching their natural frequencies. These events underscore the importance of understanding resonance not just scientifically, but practically. Engineers must consider resonant frequencies when designing buildings, aircraft, and machinery to ensure that external vibrations do not inadvertently amplify internal oscillations. Despite these dramatic examples, resonance is fundamentally an energy-matching process. When a system's natural rhythm aligns with an external rhythm, energy flows with surprising efficiency. This principle unites mechanical, acoustic, electromagnetic, and quantum systems under a single conceptual framework. In many ways, resonance reveals a deeper truth. The universe is full of rhythms, and systems respond most strongly when those rhythms align. Resonance also highlights an aesthetic side of physics. There is beauty in the idea that a system recognizes its own frequency in the world around it. A glass can break when a singer holds a note matching its resonant frequency, not because the note is loud, but because the glass vibrates in perfect sympathy. A faint radio signal can be separated from noise because a resonant circuit knows precisely how to respond to it. A star can reveal its interior because its layers vibrate in harmonious patterns. Across scales and contexts, resonance is the universe amplifying its own music. This chapter, like the previous ones, has explored oscillations and waves, but resonance adds a new layer. Where oscillation describes the motion of a single system, and waves describe the propagation of patterns through space, resonance describes the interaction between systems. It shows that the universe is not a collection of isolated motions, but a network of rhythms capable of influencing and amplifying one another. As you reflect on the idea of resonance, you may feel its metaphorical weight as well. Just as physical systems respond more deeply to rhythms that match their natural frequencies, you, too, may find that certain experiences, ideas, or people resonate with you more strongly than others. Some thoughts amplify your energy, others fade without much effect. In a world filled with countless vibrations, literal and figurative, finding resonance can bring clarity, connection, and calm. And in this moment, as your own thoughts settle into gentler rhythms, you might sense how resonance shapes not only the physical universe, but also the inner one. You are part of a cosmos that vibrates in patterns large and small, and somewhere within that vastness, your own quiet frequency finds its place. Chapter 6. Oscillations in living systems, heartbeats, brainwaves, and biological rhythms. Life, when viewed closely, is a tapestry of oscillations. Even though living organisms appear composed of tissues, cells, and molecules, they are equally composed of repeating rhythms. These rhythms regulate when we sleep and wake, how our hearts beat, how neurons communicate, how hormones rise and fall, and how countless internal processes maintain the delicate balance necessary for survival. Oscillations in living systems are not incidental details. They are structural, functional, and deeply embedded in biological evolution. To understand life scientifically is, in part, to understand the patterns that repeat within it. One of the most familiar oscillations is the human heartbeat. The heart is a muscular pump that contracts and relaxes in a rhythmic cycle. Each beat propels blood through the circulatory system, delivering oxygen and nutrients to tissues and removing waste products. This rhythmic contraction does not arise from mechanical clockwork, but from electrical oscillations within specialized cardiac cells. These cells, located in the sinoatrial node, generate regular electrical impulses that spread through the heart, triggering coordinated contraction. The regularity of this rhythm is maintained through the flow of ions, charged particles, crossing cell membranes in a repeating sequence. These ionic currents form a natural biological oscillator, a living pacemaker that sustains the rhythm of circulation. The heartbeat is modulated by external factors such as exercise, emotional state, and temperature, but its core rhythmicity persists independently. This persistence is evidence of an intrinsic oscillator, one that emerges from the interplay of ion channels, electrical potentials, and cellular geometry. When the rhythm becomes too fast, too slow, or irregular, it is not only a medical concern, but a disruption of one of the body's foundational oscillations. Yet even these irregularities follow patterns that can often be traced to subtle changes in the underlying oscillator. Cardiology is, in many ways, the study of how resonance and oscillation principles manifest in tissue and how they can destabilize under certain conditions. The brain contains another rich domain of oscillatory behavior. Neurons communicate through electrical impulses called action potentials, which arise from rapid shifts in membrane potential. But beyond the firing of individual neurons, the brain produces large-scale oscillations known as brainwaves. These oscillations represent coordinated activity across populations of neurons, creating rhythmic patterns measurable on the scalp through electroencephalography. Brainwaves come in various ranges, each associated with different states of consciousness. Slower oscillations are linked to sleep and deep rest, while faster oscillations correspond to alertness, focused attention, and complex cognitive processing. These neural oscillations do not exist merely as byproducts. They play functional roles in information processing. Rhythmic synchrony among neuronal populations allows different regions of the brain to coordinate timing, integrate sensory inputs, and regulate the transmission of signals. Certain oscillatory patterns are associated with learning and memory. Others help the brain transition between states, such as wakefulness, dreaming, and deep sleep. The brain, through its oscillations, creates structured timing that shapes consciousness itself. Beyond the nervous system, oscillations influence cellular processes across the body. Cells contain internal biochemical oscillators that regulate the production and breakdown of molecules. Many of these oscillations form feedback loops, where the output of one reaction influences the input of another in a repeating cycle. One of the most important examples is the circadian rhythm, a roughly 24-hour cycle that governs sleep-wake patterns, metabolism, hormone release, and body temperature. Circadian rhythms are controlled by molecular clocks within cells, composed of genes and proteins that oscillate in concentration throughout the day. These internal clocks synchronize to external cues, such as light and temperature. When external cues shift, such as during jet lag or shift work, the biological oscillators must gradually readjust. This desynchronization illustrates how deeply oscillations govern biological function and how sensitive these rhythms are to environmental changes. Even simpler organisms exhibit oscillatory behavior. Many single-celled organisms rely on oscillations to coordinate movement or regulate nutrient uptake. Bacteria communicate using chemical signals that oscillate in concentration, enabling populations to act collectively. Some species of algae synchronize their movements in rhythmic waves, responding to changes in light or temperature. Oscillations are not an invention of complex animals. They are woven into the most ancient biological processes. Muscles, too, rely on oscillatory patterns. Although muscle contractions are often described in terms of tension and release, their underlying mechanism involves the rapid, repeating binding and unbinding of molecular motors. These motors convert chemical energy into motion through cycles that repeat thousands of times per second. Muscle tremors, shivering, and fine motor control all arise from oscillatory firing of motor neurons and the rhythmic actions of muscle fibers. Without these cycles, movement as we experience it would be impossible. Hormonal rhythms form another layer of biological oscillation. The endocrine system releases hormones in pulses rather than continuous streams. Hormone levels rise and fall in patterns regulated by feedback loops. Cortisol, often called the stress hormone, follows a daily rhythm, peaking in the morning and decreasing through the evening. Melatonin rises at night to promote sleep. Growth hormone is released in pulses linked to deep sleep stages. Even reproductive hormones follow oscillatory cycles. These rhythms help maintain homeostasis, the body's internal equilibrium, and disruptions can have far-reaching physiological consequences. Breathing is another oscillatory process essential to life. The respiratory cycle brings oxygen into the body and removes carbon dioxide in a repeating rhythm. Although breathing can be consciously controlled, it is primarily regulated by neuronal oscillators in the brainstem. These oscillators monitor carbon dioxide levels in the blood and adjust breathing rates accordingly. Breath is one of the most accessible rhythms humans experience, and practices such as meditation draw on the calming effect of aligning conscious awareness with this natural oscillation. Immune systems also depend on oscillatory timing. Some immune responses occur in pulses, allowing the body to balance defense and repair. Fever involves temperature oscillations regulated by chemical messages that shift in response to infection. Many immune cells migrate in rhythmic patterns, and inflammation often follows cyclical phases of activation and resolution. These oscillations contribute to efficient defense while preventing excessive responses that could damage healthy tissues. In the developing embryo, oscillatory processes guide the formation of the body. During early development, segments of the spine emerge in repeating units controlled by a genetic oscillator known as the segmentation clock. This mechanism generates waves of gene expression that sweep across developing tissues, carving out the repeating pattern of vertebrae. The existence of such a biological clock demonstrates that oscillations can shape not only physiology but also anatomy itself. On an even smaller scale, oscillations appear within individual molecules. Proteins often shift between different conformations in rhythmic cycles, enabling them to perform tasks such as transporting ions, transmitting signals, or catalyzing reactions. These molecular oscillations operate at timescales far beyond conscious perception, yet they determine the flow of energy and information inside cells. Throughout all these examples, one theme emerges. Oscillations in living systems are not isolated events. They are interconnected. The heartbeat responds to hormonal rhythms. Brain waves shift according to circadian timing. Breathing interacts with emotional state. Cellular clocks influence immune responses and metabolism. When these oscillations align and reinforce one another, the organism thrives. When they fall out of sync, the result can be fatigue, illness, or cognitive disruption. Health depends not only on the presence of biological rhythms, but on their coherence. This chapter differs from earlier ones by focusing on oscillations not in mechanical systems, electromagnetic waves, or quantum structures, but in organisms. Yet the underlying physics remains closely related. Whether ions move across membranes, proteins shift shape, or neurons synchronize their firing, the principles of periodic motion apply. Biological oscillations arise from feedback loops, energy exchanges, and regulatory mechanisms that follow the same broad rules as other oscillators. They require restoring forces, they exhibit characteristic frequencies, and they interact with external rhythms. Life, then, can be seen as a complex system of nested oscillations, each with its own pace and function. Some are rapid, like neural firing. Some are slow, like circadian rhythms. Some span entire lifetimes, like developmental cycles. Together, they create a dynamic equilibrium, a living harmony in which timing is as essential as structure. As you reflect on these ideas, it becomes clear that the rhythms of life are not abstractions. They are part of your experience. Your heartbeat is a reminder of constant motion beneath stillness. Your breath carries its own soothing oscillation, rising and falling with quiet precision. Even your thoughts move in patterns shaped by the brain's internal waves. You exist within a moving, rhythmic world, and these oscillations continue, whether you notice them or not. And perhaps there is comfort in that. Life does not depend on continuous effort or conscious control. It unfolds in cycles, sustained by rhythms older than memory. As you let these thoughts settle, you may feel those rhythms within you, a gentle, steady pulse shared with all living things, reminding you that you are part of a vast, interconnected pattern that never truly stops. Chapter 7. Planetary and Cosmic Oscillations, the Universe in Motion. When we lift our eyes to the night sky, the universe may appear still, a quiet dome of stars frozen against the darkness. Yet the cosmos is anything but silent or motionless. Every planet, moon, star, and galaxy is engaged in continuous oscillation. These oscillations are not merely movements in space. They are responses to forces, internal vibrations, rhythmic patterns carved into nature by gravity, rotation, magnetism, and the physics that governs matter at every scale. The universe breathes and trembles in ways both subtle and dramatic, and through these oscillations it reveals its structure, history, and evolution. Planetary motion is one of the most accessible examples of cosmic oscillation. Although planets orbit their stars in paths that repeat over long periods, these orbits are not simple circles, but elliptical trajectories shaped by gravitational interplay. Each orbit is a kind of oscillation in space, a repeating cycle that brings a planet alternately closer to and farther from its star. This motion follows precise laws rooted in gravity, and the cycle continues until disturbed by interactions with other celestial bodies. Even these disturbances, the gravitational tugs from neighboring planets, introduce additional oscillations. The orbital paths slowly shift, tilt, and precess, creating long-period variations that astronomers measure to understand the stability and evolution of planetary systems. Moons exhibit their own oscillatory behavior. The moon's orbit around Earth wobbles slightly due to gravitational influences from the sun, producing a phenomenon known as libration. Libration causes us to see slightly different portions of the lunar surface over time, as though the moon were gently nodding in acknowledgement of its celestial partners. This subtle oscillation provides a reminder that even within the apparent constancy of the night sky, small rhythmic motions unfold continuously. Tidal forces create another layer of oscillation. Gravity from the moon and the sun pulls on Earth's oceans, generating the rise and fall of tides. But tides are not simple repetitions. They involve complex oscillatory patterns influenced by ocean basins, coastline geometry, and Earth's rotation. The water in large basins sloshes back and forth in rhythms known as tidal resonances, similar to liquid oscillating in a partially filled container. These natural frequencies shape the timing and height of tides in different regions. Some coastlines experience dramatic tidal swings because the incoming tidal wave matches the resonant frequency of the bay or estuary. Planetary interiors also vibrate. Earth experiences seismic oscillations when tectonic plates shift and release stored energy. Earthquakes generate seismic waves that propagate through the planet. After significant seismic events, Earth can ring like a bell, vibrating in modes called normal modes. These oscillations are extremely subtle, but sensitive instruments detect them as rhythmic variations in Earth's shape and gravitational field. By studying these oscillations, scientists can infer the structure of Earth's interior, including the size of its core and the properties of its mantle. Similar techniques are applied to other planets and moons using landers and orbiting spacecraft. Stars vibrate as well, though on scales far greater than planetary tremors. The Sun is constantly engaged in oscillations driven by pressure waves traveling through its interior. These waves, known as P-modes, cause the surface to ripple in patterns that resemble vibrations on a musical instrument. Although the movement is tiny, mere meters across the surface, it contains a wealth of information about the Sun's structure. By analyzing the frequencies and amplitudes of solar oscillations, scientists can map the Sun's inner layers, uncovering how temperature and density vary with depth. This field, known as helioseismology, treats the Sun as a vast resonant object, responding to internal energy flow with rhythmic motion. Other stars oscillate too. In certain stars, oscillations can become dramatic, causing the star's brightness to vary over time. Variable stars, such as Cepheids, pulsate in cycles that repeat with remarkable regularity. These pulsations occur because layers within the star heat and cool periodically, causing the star to expand and contract. The period of pulsation is linked to the star's intrinsic luminosity, making Cepheids invaluable tools for measuring cosmic distances. Their oscillations reach across the universe, providing a cosmic yardstick by which astronomers estimate the scale of galaxies and the expansion rate of the cosmos. Beyond individual stars, galaxies also experience oscillations. When galaxies interact or collide, gravitational forces can set them trembling on vast scales. A passing galaxy may tug on another, causing its stars to shift in oscillatory patterns around the galactic center. Waves of density may propagate through galactic disks, shaping the formation of spiral arms. These spirals are not fixed structures. They are patterns that move through the galaxy like ripples on a pond. The stars themselves migrate through these ripples, contributing to the long-term evolution of galactic structure. On even grander scales, oscillations appear in galaxy clusters. When clusters merge, the intracluster gas, the hot, diffuse plasma between galaxies, sloshes back and forth for millions of years. These oscillations can produce observable patterns in X-ray emissions, revealing how energy is distributed across the cluster. The largest structures in the universe, such as the cosmic web, also contain oscillatory signatures. In the early universe, pressure waves traveled through the primordial plasma, leaving imprints known as baryon acoustic oscillations. These imprints are visible today in the distribution of galaxies, encoding information about the universe's expansion history and helping to constrain models of dark energy. Oscillations occur not only in matter, but also in spacetime itself. Gravitational waves, ripples in the curvature of spacetime predicted by general relativity, represent one of the most profound oscillatory phenomena ever discovered. When massive objects like black holes or neutron stars spiral toward each other, they generate waves that propagate through the universe at the speed of light. These waves stretch and compress space-time, distorting distances by minuscule amounts. The detection of gravitational waves confirmed that space-time can vibrate, carrying information about some of the most energetic events in the cosmos. Unlike electromagnetic waves, gravitational waves are not easily absorbed or scattered, allowing them to pass through matter unimpeded. They carry with them the signature of the cosmic dance that created them. Planets and stars can experience oscillations driven by magnetic fields as well. In the Sun, magnetically driven oscillations contribute to the solar cycle, leading to periodic variations in sunspot activity. These cycles, lasting roughly 11 years, are driven by oscillations in the solar magnetic field, causing changes in the Sun's outer layers. These magnetic oscillations influence space weather, affecting Earth's magnetosphere and impacting satellites, communication systems, and power distribution networks. Even the rotation of celestial bodies contains oscillatory subtleties. Earth's rotation is not perfectly steady. It experiences slight wobbles known as nutation and precession. These oscillations arise from gravitational interactions with the Moon and the Sun, as well as from mass redistribution within Earth's interior. Over long periods, these rotational oscillations shape Earth's climate cycles by altering the distribution of sunlight across latitudes. The rhythms of ice ages, seen through geological records, are linked to these subtle oscillations in Earth's orientation. The concept of resonance also appears on cosmic scales, influencing the stability of planetary systems. Orbital resonances occur when two bodies exert periodic gravitational forces on each other, reinforcing their motions. Some resonances stabilize orbits, while others destabilize them. In the solar system, resonances shape the distribution of asteroids, creating gaps and clusters within the asteroid belt. In exoplanetary systems, resonances can lock planets into synchronized motion, revealing the gravitational choreography of distant worlds. Cosmic oscillations also appear in the distribution of cosmic microwave background radiation, the faint afterglow of the Big Bang. Slight temperature variations in this radiation reflect oscillations in the primordial plasma that filled the early universe. These oscillations contain information about the ratio of matter to radiation, the density of dark matter, and the geometry of space-time itself. They are echoes of vibrations that occurred long before stars or galaxies existed, preserved across billions of years as a fossil record of the universe's earliest rhythms. Throughout this chapter, the focus shifts from the oscillations of living organisms, which were the subject of the previous chapter, to the oscillations of planets, stars, galaxies, and space-time. Although the scales differ dramatically, the underlying principles of oscillation persist. Systems respond to forces, move away from equilibrium, and return again, creating patterns that repeat across time. Whether through seismic waves shaking the crust of a planet, pressure waves traversing the interior of a star, or gravitational waves moving through the fabric of space-time, the universe expresses itself through motion that cycles and returns. When we view the cosmos as a collection of oscillations, our understanding deepens. The universe becomes not a static expanse, but a dynamic, evolving system filled with rhythms. Each oscillation carries information about a star's density, a planet's interior, a galaxy's formation, or the structure of space-time itself. Scientists decode these rhythms to reconstruct the story of the universe, tracing how it has changed from its earliest moments to the present day. As you reflect on cosmic oscillations, there's a quiet comfort in recognizing that even the largest structures follow patterns. Stars pulse, planets wobble, galaxies ripple, and space-time hums with distant waves. You too are part of this vast network of motion. Just as your breath rises and falls, the universe moves in cycles far older and slower than any human life. And in that gentle mirroring between the rhythms of the cosmos and the rhythms within you, there is a reminder that stillness and motion coexist, shaping everything from the smallest moment of awareness to the largest structures ever born. Chapter 8. Gravitational waves, ripples in the fabric of space-time. When Einstein formulated the theory of general relativity, he introduced a radically different way of understanding gravity. Instead of treating gravity as a force that acts at a distance, he described it as the bending and stretching of space-time itself. Matter tells space-time how to curve, and curved space-time tells matter how to move. This elegant idea not only replaced centuries of gravitational thought, it also predicted new phenomena that no one had ever observed. Among those predictions was something extraordinary, that massive objects in motion could create disturbances in the curvature of space-time, disturbances that propagate outward as waves. These waves are known as gravitational waves. They are not waves in air or water or any material medium. They are waves of space-time itself. To imagine them, picture space-time as a flexible surface. If two massive bodies orbit each other, they do not simply move within space-time, they stir it, creating ripples that travel outward at the speed of light. These ripples are incredibly faint by the time they reach Earth, distorting distances by amounts far smaller than the width of an atomic nucleus. Yet their existence means that space-time is not rigid or fixed. It can flex, vibrate, and carry energy across vast cosmic distances. Gravitational waves arise whenever mass accelerates asymmetrically. A single object moving at constant velocity does not produce waves. But two massive objects orbiting each other, such as a pair of neutron stars, create a constantly changing gravitational field. This variation propagates through space-time in all directions. The result is a continuous emission of gravitational energy carried away by waves. As the system loses energy, the orbiting objects move closer together, spiraling inward until they eventually merge. These theoretical predictions remain beyond experimental reach for a century. Detecting gravitational waves required measuring unbelievably small changes in distance. Only with advances in laser technology, interferometry, and vibration isolation did such measurements become possible. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was designed specifically for this purpose. Its detectors use long tunnels in which lasers travel back and forth, reflecting between mirrors. When a gravitational wave passes through Earth, it subtly stretches space in one direction and compresses it in another. This tiny distortion alters the length of the laser paths, creating a measurable interference pattern that reveals the wave's signature. The first direct detection of a gravitational wave marked a turning point in physics. It confirmed a key prediction of general relativity and opened a new window into the cosmos. The wave originated from the merger of two black holes billions of light years away. As the black holes spiraled inward, they released enormous amounts of energy in the form of gravitational waves. By the time these waves reached Earth, they were vanishingly small, yet still detectable as a faint whisper in space-time. This detection was not merely a scientific milestone, it was the beginning of gravitational wave astronomy. Gravitational waves carry information that cannot be obtained from light. Light interacts with matter, can be absorbed, scattered, or blocked, and does not escape from the event horizons of black holes. Gravitational waves, by contrast, pass through matter almost unhindered. They arrive at detectors bearing an imprint of the systems that created them. From these waves, scientists can deduce the masses, spins, and orbital properties of merging objects. They can reconstruct the final moments before two black holes collide, a region of spacetime that is otherwise invisible. The merging of neutron stars creates even richer gravitational wave signals. Neutron stars are incredibly dense remnants of massive stars, composed mostly of tightly packed neutrons. When they orbit each other, their mutual gravity generates powerful waves, similar to black hole mergers. But neutron stars also contain matter that can emit light, unlike black holes. The detection of gravitational waves from a neutron star merger, followed by observations of light from the same event, allowed scientists to explore the physics of ultra-dense matter, the behavior of heavy elements, and the dynamics of nuclear processes that occur under extreme conditions. Gravitational waves also have a unique polarization pattern, meaning they stretch and compress space in characteristic ways. This pattern differs from the polarization of electromagnetic waves and allows gravitational wave detectors to distinguish true signals from noise. By using multiple detectors around the world, such as LIGO in the United States and Virgo in Europe, researchers can triangulate the location of a gravitational wave source. This enables astronomers to coordinate observations with telescopes across the electromagnetic spectrum. Beyond mergers of compact objects, other events in the universe produce gravitational waves. Supernova explosions, when massive stars collapse and explode, may generate waves through asymmetries in their collapse. Rapidly rotating neutron stars with slight imperfections on their surfaces may emit continuous gravitational waves. Even the inflationary phase of the early universe, a period of extremely rapid expansion, could have created primordial gravitational waves. Detecting these ancient waves would provide insight into the universe's earliest moments, when quantum fluctuations in space-time were stretched to cosmic scales. Gravitational waves also shed light on black holes themselves. Before their detection, black holes were known primarily through indirect evidence, the motion of nearby stars, accretion disks, and X-ray emissions. But gravitational waves offer a direct measurement of black hole properties. The final ring-down phase, when a newly merged black hole settles into its stable state, produces a series of oscillations that depend on the black hole's mass and spin. These oscillations are governed by the geometry of space-time around the black hole and align perfectly with predictions of general relativity. Observing them confirms that black holes behave as described by the theory and that their extreme curvature does not introduce unexpected deviations. At their core, gravitational waves demonstrate that space-time is dynamic. They reveal that the universe is not a static backdrop, but a flexible medium through which energy travels. Just as electromagnetic waves are vibrations of electric and magnetic fields, gravitational waves are vibrations of spacetime itself. This concept challenges intuition because spacetime seems intangible, yet physics shows it to be a physical entity capable of complex behavior. The amplitude of gravitational waves decreases with distance, spreading out as they travel across the cosmos. This characteristic ensures that the universe does not fill with uncontrolled oscillations, yet it also means that only the most violent cosmic events create waves strong enough to reach us. Black hole mergers, neutron star collisions, and enormous gravitational disturbances reflect processes so vast and energetic that they reshape spacetime on a universal scale. The mathematics behind gravitational waves is rooted in differential geometry and tensor analysis, the language of general relativity. These equations describe how spacetime curvature evolves when massive objects accelerate. The wave solutions naturally arise from Einstein's field equations when examined in regions far from the sources, where curvature becomes small but not negligible. In this regime, spacetime behaves almost like a stretched membrane, allowing waves to travel freely. Gravitational wave astronomy is still in its early stages. With continued improvements to detectors, scientists hope to observe a broader range of sources. One goal is to detect higher frequency signals, or signals from continuous sources such as spinning neutron stars. Another is to capture gravitational wave backgrounds, a faint hum created by countless distant events. Space-based detectors, such as the proposed laser interferometer space antenna, aim to capture lower frequency waves inaccessible from Earth due to seismic noise. These waves could arise from massive black hole mergers or even from processes that occurred shortly after the Big Bang. The discovery and study of gravitational waves connects the smallest scales of quantum fluctuations with the largest scales of cosmic dynamics. It reinforces the unity of nature, suggesting that the laws governing elementary particles and the laws governing galaxies belong to the same coherent framework. Gravitational waves offer a narrative written in the language of spacetime, a record of motion, collision, and transformation. As you reflect on this, there's a quiet realization that the universe is never still. Even in the emptiest regions of space, ripples pass through, carrying stories of distant events. These waves cross galaxies, travel through clusters, and slip silently through planets and stars. And eventually, after unimaginable distances, they arrive here, brushing against the fabric of your own world. You are living in a universe that vibrates, a universe where even space itself responds to movement. And in the same way that gravitational waves stretch and compress space-time, your own experiences, small and large, shape the contours of your inner world. Just as space-time bends gently in response to distant motions, you too are shaped by forces subtle and complex. In this vast cosmic web of motion, you are not separate from the universe's rhythms. You are woven into them, carried quietly along by waves that began long before you were born and will continue long after you are gone. Chapter 9. The Quantum Field Symphony: Why Everything Vibrates at the Deepest Level. At the frontier of modern physics lies a picture of reality that is both profoundly abstract and astonishingly elegant. It tells us that the universe at its deepest level is not made of solid particles or discrete bits of matter, but of fields, continuous, ever-present, and capable of vibrating in countless ways. These fields fill all space, even the regions we call empty. They have no gaps, no boundaries, no places where they do not exist. Every particle, every force, every atom, and every phenomenon we observe emerges from the oscillations of these underlying quantum fields. To say that everything vibrates at the deepest level is not a metaphor. It is a literal description of how the universe works. To understand this, it is helpful to shift from the classical picture of particles to the quantum field picture. In classical physics, particles were considered the fundamental constituents of matter, tiny, indivisible units that move through space and interact through forces. But quantum mechanics revealed that particles behave in ways inconsistent with this simple image. They act like waves in some situations, particles in others, and sometimes like both at once. Their behavior cannot be fully captured by the motion of discrete solid objects. Instead, what physicists discovered is that particles appear wherever an underlying field is excited. In quantum field theory, every type of particle is associated with a specific field. There is an electron field, a photon field, a quark field, a Higgs field, and many others. These fields fill all of space, and the particles we observe are localized excitations, tiny ripples in these fields. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. A quark is a ripple in the quark field. Even empty space is not truly empty. The fields are still present, still capable of oscillation, and still fluctuating due to quantum uncertainty. Quantum fields have a ground state, the lowest possible energy configuration, but even this state is not motionless. Because of the Heisenberg uncertainty principle, the fields cannot remain perfectly static. Their values fluctuate slightly, creating what physicists call vacuum fluctuations. These fluctuations mean that the quantum vacuum is an active, dynamic environment rather than a passive void. It seethes with short-lived excitations that appear and disappear too quickly to be observed directly. Yet their effects can be measured in phenomena such as the Casimir effect, the Lamb shift, and the behavior of particles in high-energy experiments. Every field has characteristic modes of vibration, analogous to how a musical string can vibrate in harmonics. But quantum fields differ in one essential way. Their allowed vibrations are quantized. They can only oscillate with certain discrete energies. When a field vibrates with the lowest allowed energy, we interpret the excitation as a single particle. Higher energy vibrations correspond to additional particles or particles with greater momentum. This quantization unifies particles and waves, showing that they are not separate entities, but manifestations of the same deeper structure. The interactions between quantum fields create the forces we observe. When the electromagnetic field interacts with the electron field, the result is what we call electric charge and the electromagnetic force. The photon, the excitation of the electromagnetic field, mediates this interaction, transmitting energy and momentum between charged particles. Similar principles apply to the strong and weak nuclear forces, each arising from the interplay of specific quantum fields. Even gravity, although not yet fully unified with quantum field theory, can be described in terms of oscillations in spacetime, suggesting that spacetime itself may possess quantum degrees of freedom. The Higgs field offers one of the clearest illustrations of how a field can shape reality. Unlike other fields, the Higgs field maintains a non-zero value even in its lowest energy state. This continuous presence permeating all of space interacts with particles moving through it, giving them mass. In this picture, mass is not an intrinsic property of matter, but the result of how particles couple to the Higgs field's constant background. The discovery of the Higgs boson, a ripple in the Higgs field, confirmed that this field truly exists. The fact that the Higgs boson is itself a vibration reinforces the idea that the universe is a symphony of oscillations layered within one another. Quantum fields are also responsible for phenomena that challenge everyday intuition. One example is particle creation near strong gravitational fields, such as those around black holes. According to quantum field theory in curved spacetime, intense gravitational curvature can separate vacuum fluctuations, allowing one member of a particle-antiparticle pair to escape before they recombine. This process leads to what we call Hawking radiation. The idea that black holes slowly evaporate over time arises entirely from quantum fields and their persistent oscillations. Another striking implication of quantum fields is that particles can transform into one another under certain conditions. In particle accelerators, high-energy collisions excite fields to such extremes that new particles materialize from the energy. These particles are not created from nothing. They emerge from the fields, which can be energized into different excitation patterns. The famous relationship between mass and energy becomes vividly real in this context. Energy pumped into a field can manifest as particles with mass, and those particles can decay back into field energy. Even the stability of matter depends on quantum vibrations. Electrons in atoms occupy quantized orbitals, standing wave patterns in the electron field shaped by the electromagnetic interaction with the nucleus. These orbitals prevent electrons from spiraling inward and collapsing into the nucleus. The atom's structure is therefore a quantum phenomenon sustained by the oscillatory nature of the electron field. Without these inherent vibrations, atoms could not exist. On larger scales, quantum field oscillations shaped the early universe. During cosmic inflation, quantum fluctuations in the fields that permeated the infant universe were stretched to cosmic sizes. These fluctuations seeded the distribution of matter that eventually formed galaxies, stars, and planets. The largest structures in the universe owe their existence to microscopic quantum vibrations amplified across unimaginable distances. The quantum fields, although mathematically abstract, behave like physical entities. They store energy, they carry momentum, they can interfere with one another, and they can resonate. In fact, resonance in quantum fields is essential for many particle interactions. When the energy provided to a system matches the natural frequency of a field mode, the field responds strongly, leading to particle production or enhanced interaction rates. This is analogous to striking a tuning fork at exactly the right pitch, but instead of creating sound, the resonance produces fundamental particles. Quantum fields also merge physics with information. Because fields fluctuate, and because particles are excitations of these fields, the universe can be understood as an ever-changing configuration of information stored in the field's oscillatory states. These oscillations evolve according to precise mathematical laws, encoding the structure and behavior of everything from photons streaming through space to the nuclei in the atoms of your body. Despite their complexity, quantum fields are consistent with the idea that the universe is unified at its foundation. Every particle species is just one way a field can vibrate. Every force is an expression of how fields influence one another's oscillations. The fabric of spacetime itself bends and shifts in response to energy carried by these fields. In this view, the universe is not composed of pieces that exist independently, but of patterns and fields that interweave seamlessly. As with earlier chapters, it is important to avoid repetition. We have already discussed vibration in atoms, matter, and spacetime. But here, the focus is deeper, not on the objects that vibrate, but on the fields that give rise to the objects. Quantum field theory is the level beneath atoms, beneath molecules, beneath spacetime curvature. It reveals that vibration is not something matter merely does. It is something matter is. Everything we perceive, everything that exists, is a structured pattern of oscillation in fundamental fields. And perhaps this leads to a quiet reflection. If the universe is a symphony of vibrations, then every moment of your existence is supported by rhythms far older, deeper, and more intricate than anything you can perceive. Every atom in your body, every spark of thought in your mind, every breath you take is sustained by fields that vibrate continuously. You are, in a literal sense, part of the universe's ongoing music, woven into a cosmic harmony that stretches across space and time. In this vast quantum tapestry, you are not separate from the universe's motion. You arise from it. And as you rest now, perhaps you can feel a hint of that deep connection. A reminder that even in stillness, you are carried by waves that never cease. Chapter 10. The Universe is a Wave, What Oscillation Says About Reality. By now, after exploring oscillations from atoms to galaxies, a deeper pattern begins to emerge. The idea that the universe contains waves is no longer surprising. Waves of light, waves of sound, waves of gravity, quantum waves, waves in stars, waves in matter. But the more one follows this path, the more profound the realization becomes. Waves are not just in the universe. At the deepest level, the universe is a wave. Or perhaps, more precisely, it is an intricate and continuous collection of wave-like processes, oscillations woven together into the reality we experience. To understand this claim in a scientific sense, we begin with fundamental principles of physics. Every known physical system, from a vibrating violin string to a quantum field filling space, has natural modes of oscillation. These modes arise from the system's internal structure and the constraints imposed by the forces that govern it. The mathematics that describes oscillations is deeply embedded in nearly every branch of physics. The equations that govern the behavior of electromagnetic fields, gravitational waves, atomic orbitals, and the quantum fields beneath all matter share a striking characteristic. They all take the mathematical form of wave equations. Wave equations describe how disturbances propagate in space and time. They encode how something that is displaced from equilibrium moves, spreads, and interacts. What differs from system to system is what is oscillating: the electric and magnetic fields, the curvature of space-time, the density of a stellar interior, or the amplitude of a quantum field. What remains constant is the fundamental structure of change expressed as oscillation. One of the deepest examples of this universality lies in quantum mechanics. In quantum theory, the behavior of any particle is described by a mathematical entity called the wave function. The wave function itself is not a physical wave in the classical sense. It does not ripple through space like a water wave. Instead, it encodes the probability distribution for finding a particle in a particular configuration. Yet the wave function evolves through time according to the Schrödinger equation, which is essentially a form of wave equation. Wave-like behavior is therefore fundamental to the very concept of a particle. Electrons, photons, quarks, and even atoms can interfere with themselves, diffract around obstacles, and exhibit patterns characteristic of waves. This wave-like nature does not disappear as systems grow larger. In carefully controlled laboratory conditions, even large molecules have shown interference patterns when passed through devices that split and recombine their wave-like states. The fact that matter of increasing complexity continues to exhibit behavior governed by wave equations suggests that the wave nature of reality is not limited to the microscopic domain. It is simply that wave-like effects become increasingly difficult to observe as systems interact with their surroundings and lose coherence. Another important aspect of universal oscillation arises from relativity. General relativity describes gravity not as a force but as a curvature of spacetime. In this framework, disturbances in curvature propagate as gravitational waves, carrying energy and information across the universe. The equations describing gravitational waves resemble those describing waves in other physical systems, even though they arise from a theory of geometry rather than a theory of forces. This structural similarity implies that the wave-like behavior of spacetime is not in conflict with the wave-like behavior of quantum fields. Both emerge from equations that possess oscillatory solutions. If one examines the early universe, the picture becomes even more striking. In the first moments after the Big Bang, quantum fluctuations in energy density were amplified by rapid cosmic inflation. These fluctuations oscillated and produced patterns in the cosmic microwave background radiation, the faint afterglow of the early universe. The distribution of galaxies today still carries the imprint of these early oscillations. Structures on the largest scales in the universe arise from the interplay of expanding space-time and oscillating quantum fields. The cosmos we see now is, in a very real sense, frozen in music from the earliest moments of existence. What is remarkable is that across all of these examples, oscillations do not merely describe physical behavior, they explain it. Waves are not just patterns imposed on matter and spacetime. They reveal what matter and spacetime are. When physicists describe the electron as a vibration of an underlying field, or describe gravitational waves as vibrations of spacetime, they are pointing to a unifying principle. The world is built from dynamic processes that repeat, resonate, and interact in rhythmic ways. Yet within this unified picture, there is also diversity. Different fields have different frequencies and excitation modes. The electron field vibrates differently than the photon field. The gravitational field oscillates at wavelengths billions of times larger than those of visible light. The early universe resonated with modes that stretched across cosmic distances. Each field forms a distinct part of a cosmic symphony, each contributing its own timbre, rhythm, and structure. The universe becomes not a static arrangement of particles, but an evolving composition of vibrations. This perspective reshapes how we think about matter. If particles are excitations of fields, and fields obey wave equations, then what we perceive as things are actually temporary, localized patterns in continuous dynamic fields. A particle is not a little solid bead moving through space. It is a stable, rhythmic pattern that persists long enough to be recognized as an entity. In this sense, everything is both wave-like and particle-like, depending on how it is observed. The duality is not a contradiction, but a consequence of deeper wave behavior manifested in different conditions. Even energy itself has oscillatory character. The The relationship between energy and frequency is fundamental to quantum theory. Energy increases as oscillation frequency increases, meaning that the structure of the universe, the distribution of energy, the behavior of forces, the emergence of particles, all reflects distinctions among oscillation modes. Fields vibrate with different allowed frequencies, and these frequencies determine what kinds of excitations can exist. The idea of the universe as a wave also illuminates the interconnectedness of phenomena across scales. Oscillations influence how galaxies evolve, how atoms form bonds, how biological rhythms operate, and how quantum fields shape the matter in your body. These different domains may seem unrelated, but the recurring theme of oscillation links them intimately. A star pulses with pressure waves, a neuron fires with electrical rhythm, and a quantum field oscillates in the vacuum that fills space. They all follow patterns determined by the same laws of motion. It is also important to emphasize that waves in the universe do not move independently of one another. They interact, interfere, resonate, and sometimes cancel out. In quantum systems, interference of wave functions determines the probability of outcomes. In classical physics, resonance amplifies certain wave patterns while suppressing others. In cosmology, waves in the early universe influenced how matter clumped together under gravity. The interplay of waves across different fields generates the rich variety of structures in the universe. One might wonder whether this wave-based picture reduces the complexity and richness of reality to something overly abstract. But in truth, it enhances our understanding. Waves are not simplistic. They embody information, structure, coherence, and transformation. A wave can be simple or extraordinarily complex, depending on how it combines with others. In the same way, the universe can support both the stable order of atoms and the chaotic turbulence of galaxies. The wave nature of reality does not flatten distinctions, but allows them to arise from a common foundation. From this perspective, the universe is not made of static pieces that occasionally move. It is made of movement itself, movement that repeats, sustains, evolves, and carries information forward. If everything arises from waves, then reality is a constant unfolding of patterns, each shaped by interactions among deeper oscillations. This means that change is not an accident of nature. It is the essential nature of existence. Nothing remains perfectly still because nothing can remain perfectly still when the foundation of reality is oscillation. In the context of quantum field theory, this means the vacuum itself is dynamic. Space is filled with fluctuations that ripple even in the absence of particles. These fluctuations influence how particles interact, how forces behave, and how energy is distributed. In this way, the background of the universe participates in its evolution. The universe is not built atop a static stage. The stage itself is alive with subtle motion. As you reflect on these ideas, consider the possibility that reality is not made of objects but relationships, patterns of vibration interacting in complex ways. Every experience you have, every sensation, every thought, every breath is underpinned by oscillations that stretch across all scales of existence. You are part of a universe in motion, composed of waves that began long before you appeared and will continue long after you are gone. And perhaps there is peace in that. Just as waves travel outward from distant events, the rhythms of your own life ripple quietly through the world, leaving traces you may never fully see. In a universe defined by oscillation, you are not separate from the cosmic symphony. You are one of its notes, fleeting, gentle, but essential to the harmony of the whole. Thank you for spending this time with me, my friend. I hope these gentle waves of science helped your mind unwind and your body soften into rest. If you're still awake and want to wander a little further, another video is waiting for you right here. Quiet, slow, and ready to keep you company. But if your eyes are closing, then good night. Sleep well, and may your dreams drift softly among the stars.